Hey everybody, I'm going to give a short lesson on section 2.5, which is all about this guy, vectors. If you haven't seen that movie, it's adorable. My kids love it. So this is kind of a little intro to physics. So if you're a physics student or if you're going to go on and do a lot of calculus later in your math career, then we use vectors a lot. And I really love this topic, but this is kind of a real light treatment of them. So what is it? It's a mathematical object that has direction and magnitude. And we represent these things with an arrow. And it doesn't matter where you move the arrow to. All that matters is the direction and the magnitude. So if I draw this arrow right here, that's technically the same vector as this arrow over here because they point in the same direction and they have the same length. But if I were to draw it like this, now it's a different vector because it's pointing in a different direction and it has a different length. So it doesn't matter where you put them. All that matters is how long the arrows are and what direction they point in. So if the angle changes, that's something different. And if the length changes, that's something is different. And these are mathematical models for things that you're familiar with, like force. I put the units here. The units of force are pounds, and velocity. The units of velocity are miles per hour. And we like to draw vectors in standard position. So if you have a coordinate plane, then I'm going to put the vector right there at the origin and extend out to the point x, y. So this is the way that we draw vectors. Usually, you'll see the letter V for vector, and textbooks will make it like bold, for vector, but we can't do that. So we draw a little like arrow over the top of it like this. That's how we mean that it's a vector. So we think of numbers as being scalars. The idea behind that is if you had some kind of force like this that was represented by a vector, and then I wanted to say 2 times that vector, it should be the same vector but just twice as long. So in this context, the job that numbers are going to be doing is being rescaling the vectors. So they're just trying to be really clear about that's what the job of numbers is in this context. So because of that, we come up with a new name for numbers. So 7, it's not a number anymore. Now it's a scalar. Oh, okay. Yeah. Okay, so we model the rules for adding vectors off of the way that the rules for adding forces works in real life. So let's say that you're in a boat and you're trying to cross a river in the boat, and there's some current that's pushing down the river. So in this little picture that I've drawn right there, the little triangle thing, that's the boat. And the engine of the boat, you're driving straight across the river. So this right here represents the force on the boat from the engine of the boat. You got a little motor in your boat. And then V number 2 represents the force that's due to the current. So maybe I drew it a little bit long. That's like a really strong river. Let me draw a little bit smaller. There we go. Now it's not quite as strong a river as it was before. So V1, V2 should represent the total force on the boat. We call it the resultant. The resultant force from both the engine and the current. How does it work? So what you do is you just take this one, V number 2, and you just copy it over onto the end of V number 1. So you just make another little copy of V number 2 over there. And then the new resultant force you just do by connecting the diagonal. So these two make a kind of little box or a little parallelogram. And then right here, this red arrow represents the resultant force. So that's actually the force on the boat. And this is true. If you drive straight across the river and the water's pushing you down, you don't go straight across the river, right? You kind of go at a sort of diagonal down the river. So that's where we get these rules from. What we'd like to do is solve problems with vectors, and one thing that makes solving problems with vectors a lot easier is trigonometry. So I'm going to try to marry the concepts that we have studied so far in trigonometry with this new ideas of vectors. So what we do is we take a vector and we decompose it into two lengths. One of them is the shadow of the vector on the x-axis, and the other one is the shadow of the vector on the y-axis. So it's kind of the horizontal part of the vector and the vertical part of the vector. So these are called the components of the vector, or the projections of the vector, or the shadows of the vector. So if the tip of this vector right here is at the point x, y, then you can see this length right there is just going to be x, and that length right there is just going to be y. So we have new names for these because now we're, instead of thinking of them as just being lengths, we're now thinking of them as being vectors. So we're going to call this piece right here, this arrow that goes right along the x-axis and goes down till it's perpendicular with the tip there. We're going to call this v sub x, and that's a vector. And then also this vector right here, we're going to call that v sub y. And this is useful for us because now I can start using trigonometry to solve problems about vectors. So the point is that we write it like this. V is equal to v sub x plus v sub y. And you can see this does follow that rule where you kind of make a diagonal. So the idea behind this, one more time, is you can always take a vector and break it down into its two parts. How much of this vector is coming from the horizontal direction and how much of the vector is coming from the vertical direction. Okay, and how long are these pieces? Actually, it's not hard to see that from right triangle trigonometry. Okay, so let's just use SOHCAHTOA to set this up. So the actual arrow there is the vector, but if I pull these links out of this triangle, then they're no longer vectors, now they're just lengths. So I'm going to write the magnitude of v right there, and the magnitude of v sub y, that's just the vertical part of the vector, and then the magnitude of v sub x, that's the horizontal part of the vector. So the difference between this second picture and the first picture that I've drawn is, in the first picture, this letter v represents that arrow. When I put these absolute value bars around it, it just represents the length of the arrow. So now these are no longer vectors, these are now scalars, just how long that line is. So from SOHCAHTOA, actually I only need SO and CA here, I could say, okay, so here's theta. I could say that the sine of theta is equal to the opposite, that's the magnitude of v sub y, over the hypotenuse, that's the magnitude of v. And likewise, the cosine of theta is equal to the magnitude of v sub x divided by the magnitude of v. Okay, so here is how you break down a vector into its components. The magnitude of v sub x, okay, you can see if I just moved this, if I multiply both sides by the magnitude of v there, I would just have the magnitude of v sub x left, will be cosine theta times the magnitude of v. Always like to put my little arrows on top. And likewise, the magnitude of v sub y will be the sine of theta times the magnitude of v. Okay, so now we know how to take a vector and break it down into its two components. Okay, so here's an example problem. I've given us some vector, and since it has a units of pounds there, I know that this vector represents a force. And I also give us the angle of the vector in standard position, and we're asked to come up with the horizontal component, that's v sub x, and the vertical component, that's v sub y. So we just want their magnitude. So I'm just using this formula right here. v sub x, the magnitude of v sub x is cosine times the magnitude of v. So in this, cosine of theta times the magnitude of v. So this is going to be the cosine of 18 degrees times the magnitude of v is 50. And then for the vertical component, I'll get the sine of 18 degrees. I wrote 15. 18 degrees times 50. And then I'm just going to use my calculator to approximate this. Round your answer to 2 decimal places. Okay, so, got to make sure you're in degree mode every time. Make sure you're in degree mode. All right, so the cosine of, I like to put the number first. I'm going to write 50 cosine 18 degrees. I like to put the scalar first. We're calling them scalars now instead of numbers, all right? And then the sine of 50 times the sine of 18. Messed that up. Try again. Okay. All right. So I got round to 2 decimal places. So 47.55 and 15.45. So these will also be pounds. Okay. So yeah, that's it. So this force that's pointing at kind of a very shallow angle. Actually, I may have drawn my 18-degree angle here a little bit bigger than it really is. You can see that most of this force is in the horizontal direction, right? There's much more length in the horizontal direction, and there's really not very much length in the vertical direction right there. So the horizontal component is 47.55, and the vertical component is 45.55. You should be able to check, right? Because these pieces are all part of a right triangle. We should be able to just check that the Pythagorean theorem is gonna work. So you may just want to take a minute to just plug that into your calculator and see. Really, since we rounded, these things really should be approximately equal to each other because we rounded. So, yeah. All right, that's how vectors and components work. Okay, so there's some example problems in the homework. It's about a child on a swing, but it doesn't matter. This is an example of a problem about pendulums. So pendulums are like a weight that's suspended from a string, and you pull it over, and then you let it go, and it oscillates back and forth. Okay, so you suppose that you have the pendulum hanging from the string, and then you kind of pull it over, and you're going to just hold it there. You're not going to let it go. Okay, so because you're just holding it there and it's not moving, we say that the pendulum is at equilibrium because it's not moving. Okay. All right, so these are all of the forces that are acting on a pendulum when you're just holding it there, when it's at equilibrium. So first of all is the weight of the pendulum itself pulling down. So I chose W for the weight. That's just however heavy the ball is, okay? The second one is the tension force, right? Because when a weight is hanging on a ball, then it's pulling down on the string on whatever it's attached to, maybe the ceiling or something up there. So that force is called the tension force. And then also, since you pulled it over and you're holding it there, you're putting some force on the ball as well. We call that H. It's kind of a horizontal amount of force there. So in the problem that we're doing here, they give us the weight. They give us that the weight, the magnitude of the weight here is 46 pounds. And they tell us that the angle theta is equal to 45 degrees. And they ask us to find the magnitude of H. And they ask us to find the magnitude of T. Okay. So there's the setup of the problem. Let's just put all these things in a little picture, and then it'll make more sense to us. Okay, so here's the right triangle picture that goes with this. Okay. Okay, so there's our right triangle. So this sort of diagonal one right there, that right there, is t. So that means right here is the magnitude of t, just however long t is. The horizontal one is h, so that means this length across the bottom right there is h. Well, so the arrow along the bottom is h. The length of that arrow is the magnitude of h. And then one more, this w, the weight force pulling down. So the arrow is w, and the length of that arrow is the magnitude of w right there. So there's theta. All right, so in our problem, this is 46. Oh, I wrote degrees. That's not right. You measure your weight in degrees. Sorry, this should be pounds. So this is 46 pounds. And then we're asked to come up with t and h. So, okay, so according to right triangle trigonometry, I'm looking here. I have an adjacent side, and let's say I want to figure out what the magnitude of t is there on the diagonal. So the cosine of 45 degrees is equal to adjacent over hypotenuse. So adjacent over hypotenuse. So what does this mean? So if I multiply both sides by magnitude of t and divide both sides by cos 45, I'll have magnitude t equals 46 divided by the cosine of 45 degrees. Okay, calculator time. Okay, so I got 65.05. Let's just make sure I was in the right mode. I am in the right mode. So this means magnitude of t is approximately equal to, what do they want me to round to? Round your answers to one decimal place. So 65.1. So approximately 65.1, and this is a number of pounds. Okay, so quite a lot of tension force. And then now I need to do, I'm trying to get h here. When I look at this diagram, I see an angle, I see an adjacent side, and I see h as opposite of that. So that makes me think I need to use tangent. So the tangent of 45 is going to be the opposite over the adjacent. So this will be the magnitude of h divided by 46, the opposite over the adjacent. Okay, so multiply both sides by 46. Magnitude of h is 46 tangent 45. Okay, this should just be 46. Let's just check that. I'm getting 46. Let's see. 46 times the tangent of 45. This is kind of a special one because the computer generated this like perfectly diagonal angle there, that 45-degree angle. So yeah, we just end up with a 46 pounds here. So that's it. That's how we figured out how much of this force is going, how much tension there is on the rope, and then also how hard you're going to have to push in order to hold, in the problem it's Danny, in order to hold little Danny there up on the swing. So next problem. Okay, so there's some problems in the homework about an incline plane. So let me see if I can kind of break this down for us. So the way it works is you've got a kind of slant, all right, and that makes an angle with the horizontal there. We're calling it theta. In our problem, theta is going to be 15 degrees, so a 15-degree incline. And then there's the force due to gravity, so that's just the weight of the object pulling down. In our problem, this is a 9-pound weight. And then, so there's two other forces. Because the weight is not sliding down the inclined plane, because it is in equilibrium, that just means it's not moving. That means that there must be some force that's stopping it from sliding. So that's the force due to friction. And then also, because for every action there's an equal and opposite reaction, those two forces must combine together and be canceled out by some other force. This is the force that the ground is pushing back up on the object with. So that's why it's not just falling down. And we call that the normal force. So in our problem, they give us the weight, and they give us this angle over here in the corner, and they ask us to find the magnitude of the normal force and the magnitude of the friction force. Okay. All right, 15 degrees is not very much. All right, now I'm going to draw a perpendicular to that. So there's the normal force, and then right there is the force due to gravity. So that means this right here is the magnitude of F. This one right here is the weight, so that length is 8. It's 9 pounds in our problem. And then right here is the magnitude of the normal force. And this is 15 degrees. So what I'd really like to do is just figure out what angle goes up there in that corner. This is always 90 degrees. And if I could do that, then I could just use right triangle trigonometry to figure these out. Okay, so here's how I figured out what angle goes up into that corner. So the first thing is, let me just draw this horizontal line right there. Okay, so that line that I just drew is horizontal, and this line right here is horizontal. That means this angle right here must be the same as that angle right there, because this is a parallel bisector. So that means this angle right here, that little skinny angle right there, has to also be 15 degrees. Now this total angle right there has to be 90 degrees. So that means that this little piece right there plus whatever that angle right there is has to add up to 90, which means this one right here has to be 75 degrees. Whew! Which means now all of those, this angle right there and that 75 degree and that 90 degree are all inside of a triangle. So by the 180 degree rule, that angle right up there also has to be 15 degrees. Like all the book and like all the other videos that I found about this were just like, oh yeah, 15 goes up in that corner. And I'm like racking my brain. How do you know 15 goes up in that corner as well? So there you go. That's why. So let me clean this picture up and I'll draw it one more time. And then we can just use right triangle trigonometry. Okay, so here's a little bit cleaned up picture. 15 degrees up there in that corner, and then I got a 9 on the hypotenuse, and I'm looking for magnitude N and magnitude F. So as I look at this, I'm seeing from my 15 degree angle there, that looks like an adjacent and a hypotenuse. So the cosine of 15 degrees must be equal to the adjacent over the hypotenuse. So magnitude N must be 9 cos 15. And likewise, now I'm going to use the opposite. So the sine of 15 must be the opposite over the hypotenuse. So this must be magnitude F over 9. So magnitude F is equal to 9 sine 15 degrees. Okay, so now it's just calculator time to approximate these. So what do you get? All right, make sure that I'm in degree mode. I am. So 9 cosine 15 degrees. I got 8.7. They want me to round to 1 decimal place. And this is, I guess, a number of pounds. And then magnitude F. Okay, so I need to do 9 sine 15 degrees, 2.3. And this is also going to be a number of pounds. So that's it. Magnitude N is 8.7. Magnitude F is 2.3. Okay, good. Whew, I got it right. Okay, so there's that question. Next problem. Okay, so the next topic here is about work. And the definition of work is the magnitude of the force multiplied by the distance. That makes sense to me because you know, if you were going to do something like move a heavy stone, you know, then what would be more work for you? Well, first of all, if the stone was heavier and you had to push harder, then that would be more work. And also, if you had to move it, you know, if you had to move it 3 times as far, then it makes sense to me that you should get 3 times as much work. So the amount of work that you do should be the amount of force that you're putting on an object multiplied by the distance that you have to move it. Right, but what if you're not pushing the object entirely in the direction that you're going? Okay, so in this example, Mr. Smiley Face Man here, he's pushing the box with some force, but the issue is that he's kind of pushing down and forwards. So not all of the force that he's using is going into moving the box forwards. Some of the force that he's using is just going into pushing the box towards the ground. So the actual amount of force that he's using to push the box is just the horizontal component of the force. So that's this thing right here, right? So this is actually the amount of force that he's pushing with on the box. So the horizontal component is just going to be the magnitude of the force times the cosine of the angle between them. So if you're not pushing directly in the way that you're moving, if you're pushing at some angle, then the actual amount of force that you're using is going to be the magnitude of the force times the cosine of the angle that you're pushing it through. And then however hard you're pushing multiplied by the distance that you have to push it is going to give you the actual amount of work that you're going to do. So let's look at an example. We have one and they say that the distance, you're going to have to push this force 130 feet. Oh gosh. And then the magnitude of the force, you're pushing with 29 pounds of force, but you're not pushing, you know, you're not pushing it straight in the direction you're going, just like Smiley Face Man. You're pushing it kind of downward at an angle. So theta here is going to be 25 degrees, and this is downwards. So I don't know why they do this. They could just say theta is negative 25. I mean, we already have a way to do that. They just say 25 degrees downwards. Like, book, you made up the rules. Anyways, yeah, so the picture here is the actual magnitude of the force is 29 degrees. That's going to be 25 degrees right there. And then this length, the actual force that you're using, so that's the magnitude of the horizontal component of the force, is going to be 29 cos 25. Okay. So let's work out what that is. Am I still in degree mode calculator? Yes, I am. 29 cosine 25. So the actual amount of force is not all of the 29 degrees. It's just 26.3 of it. So it looks like they did a lot of rounding here. So we get F sub x magnitude is 26.3. So the work is going to be the actual force, 26.3, multiplied by the distance that you have to push it. That's 130 feet. So what do you get? 26.3 times 130. So you're getting 3,400. So basically 3,400. So this is approximately 3,400. And then the units of work are very strange, but these are real units. They're called foot-pounds. And the idea is that, yeah, you know, I mean, you multiply the units together, so that's the answer. 3,400 foot-pounds of work. So that seems like a lot of work to me. I feel sorry for Smiley Face Guy. So that's it. Let me know if you get stuck on the homework, and I'll see if I can come in and have a look at it and give you a hint or just help you out. So have a good day. I'll see you guys on Wednesday for the test. Please just don't hesitate. If you get stuck or you have a question or anything, just email me, and I'll do my best to get back as fast as I can.